status quo. His name? Dayton Miller. His weapon of choice, a flute. But not just any flute. This instrument held the power to unleash the ether, a pervasive medium once thought to fill the universe. Miller, a physicist by trade, a musician at heart, discovered a harmonic resonance within the ether. He found that his flute, when played with precision, could manipulate this elusive medium. His melodies, a symphony of science, had the potential to shift the very fabric of reality. However, a sinister force lurked in the shadows. The Einsteinian demons. These creatures thrived in the distortion of space-time, causing chaos and disruption. The world needed a hero, and Miller was ready to answer the call. With his
All right, hello and welcome everyone. Tonight we're going to be doing reading night for Aether Cosmology Roundtable 107. Samoa King, are you talking? Or
No, it just looks like it.
Word, gotcha. That was very confusing. All right, what's up? Nice to see you here for reading night. Tonight we're going to be getting into the superluminal Maxwell displacement current measured in the near field of a spherical capacitor. And as we go through the paper, we'll kind of read the significance of what all that means. And we'll get some nice diagrams. And if I'm not mistaken, everything in this experiment is pretty average, like regular labs and stuff should have this kind of stuff, like an oscilloscope and a Wimhurst machine. So we might be able to convince our quality assurance department to use his oscilloscope to reproduce this or something, see what happens. All right, so we'll get into it here. Superluminal Maxwell displacement current measured in the near field of a spherical capacitor. Abstract. We report herein the observed null result measuring any known finite speed in air of the one-way near-field signal and information velocity of the field displacement current between poles at a total of 1.5 meters separated poles, spherical air capacitors caused by its impulse spark discharge. Introduction. According to Maxwell's classic electromagnetic theory, a field displacement current exists between the conductive plates or two poles of every capacitor. It's important to note that the current is not the same as the electron current. The displacement current is responsible for pushing the charges in an electric circuit that exists on the poles of the capacitor. The electric field observed between the two poles of the capacitor acts effectively as a displacement charge current, shifting the electric charges traveling from one pole to the other. Even if there is an electric insulating dielectric like air in between these poles, the displacement current continues to operate. For better understanding, you can refer to Figure 1. And here we have Figure 1, the displacement current between the plates of an air capacitor responsible for pushing the charges of an electric circuit between the plates of the capacitor. So here we have a nice little integral for equation 1. As per equation 1, the current associated with the displacement field at I sub d observed during the charging or discharging of the capacitor is equal to the rate of change of the electric flux phi sub d within the electric field E present between the capacitor plates. This means that any sudden change in the electric displacement field E, as shown in Figure 1, caused by the charging or discharging of the capacitor, will propagate between the poles of the capacitor as a signal moving at a finite speed of light. Note that the current fluctuation or signal of the displacement field will produce both electromagnetic wave radiation and the longitudinal scalar field fluctuation components. You can observe this phenomenon in Figure 1, where you can see the parallel straight electric flux lines between the plates of the capacitor. The forces align with the pointing energy transfer vector, similar to the pressure vectors of an acoustic longitudinal wave or water tsunami. According to the theory of relativity, a short-range Coulomb charge longitudinal fluctuation is believed to travel at the speed of light between the plates of the capacitor in the near field. This means that the separations of the plates is multiple times the wavelength spectrum of the electrostatic field's impulse charge or discharge signal. It should be possible to observe this phenomenon. However, it has not been experimentally proven that the case for the near field, where the separation of the capacitor plates is less than one wavelength. This is typically the case for capacitors and wired electric circuits. Therefore, most displacement fields that exist between the poles of the electronic capacitor devices should be regarded as a near-field interaction. The motivation of our experiment is to do the research conducted by Walker W. and others from 1997 to 2023 in citations 1, 2, 3, and 4. Their research showed that, contrary to relativity, electromagnetic waves propagate instantaneously in the near field and reduce to the speed of light at about one wavelength from the source when transmitted between a transmitter and receiver dipole antenna pair. In our experiment, we hypothesized that the superluminal effect being studied is due to the longitudinal field component transmitted within one wavelength in the near field between the transmitter and the source, or between the transmitter, signal source, transmitter, and the receiver. So TX and RX are transmitter and receiver. This field component dies off very quickly within one wavelength distance range, and then the transverse EM wave continues on its path at the normal speed of light for a specific medium, or else the speed c in a vacuum. In addition to the aforementioned observations, Maxwell's theory and equations themselves predicted instantaneous propagation time for the displacement current, rendering it non-local in nature. See results and discussion section for clarification on that. Since our experiment operated in the near field, the observed effect could potentially be characterized as a superluminal signal, although it is important to note that the term non-local typically refers to phenomenon in the far field and does not imply the transmission of information. Next, we will present a novel tabletop experiment and its results, which specifically are focused to measure the longitudinal energy component of the displacement current of an air capacitor in the near-field propagation speeds between the two poles. The apparatus methods, section 2.1, experimental setup. Our experimental setup is based on the previous independent experiments by W.G. Gazer in citation 5, which nevertheless differs from our setup. The theoretical background we present, the measurement method that is used, and the results. We measured a finite speed 2 to 5 times the speed of c in the near field opposite to our experiment, which reports null or negative results, unable to measure the known speed of light through air around 1.003 times, or 1.0003 times slower than the speed of light in a vacuum free space.
Yeah, that's where I would stop, just for point of clarification. I think they made that as hard as possible to actually understand in terms of quantification. That expression 1.0003 times slower, does anybody know how much slower that actually is? Just by looking at it?
Couldn't tell you.
No. It's the truth is, all you have to do is apply the reciprocal to that to get the correct expression, that it is 99.97 times c in the vacuum. 99.97% of c. Let me get that straight. 99.97% of c in the vacuum of free space. That's the correct way to express that, so that people can intuitively understand what's going on here. So yeah, go ahead.
Yep. All right. Let's see here. Therefore, the instantaneous propagation speed reported, or at least consequently, depending on the time resolution, technical specifications, limits of our measuring apparatus, superluminal propagation may be many more times that the speed of c in a vacuum in the near field. Our setup is shown here in figure 2. So we got a Windhurst machine that generates a spark. This is our transmitter. And when that spark gets discharged, it gets registered here by the oscilloscope, and the timing is synchronized with the receiver here. So when this produces
one
a charge,
thing they're not showing here, I hope they make it apparent in the upcoming, because I haven't read this paper in advance yet. But notice the spark gaps, one on the left, one on the right. The one on the left firing, where there actually is an arcing going on. What they're not showing is polarity and orientation to that axis of the dotted line between them, 1.5 meters apart. You know what I mean? Is the black Mickey Mouse here on the left the positive or the negative? You know what I'm saying? That very well could have everything to do with how well the receiver receives what's going on in terms of the change and the rate of change between those 2 points in the spark gap. Does that make sense?
It does. And I don't know if they
Okay, cool.
ever say that.
I hope they do actually specify that. Anyways, get on there. Let's see what's up.
All right. So these are the transmitter and receiver is separated by 1.5 meters or 5 nanoseconds of flight time for the speed of light in a vacuum. And so the theory here is that when this discharges, it gets received it'll instantaneously read on this side too, because they're time synchronized in the machine or whatever. So when we'll get into the specs on its scope of resolution, I think it's 1 nanosecond. So anyway, so the two spherical air dielectric capacitors in series, Maxwell's displacement current field propagation experiment. Note that the transmitter and the receiver signal group velocity is measured by the two channels of the digital RIGOL 50 megahertz oscilloscope with a 1 nanosecond base resolution. The connected OSC channels probes BW is filtered to 2 megahertz maximum frequency. Thus, the wavelength is about 150 meters of the transmitter and the receiver signal, and therefore the near field is measured.
BW is bandwidth.
Thank you. TY.
Yeah, just to clarify, RIGOL, that's the maker of the actual oscilloscope. That's Regal. They're quite popular. Tektronix is the more popular rival, which is what I happen to own, just to boast.
Nice. All right, the transmitter spark gap spherical capacitor of the Windhurst machine is shown in figure A3 is aligned in a series with the receiver capacitor shown in figure 3B with a separation of 1.5 meters or approximately 5 nanolight seconds based on the speed of light in a vacuum. Together they form a single capacitor with a separation of 1.5 meters between its poles. This distance is significant and allows for the necessary delay to enable the oscilloscope to measure the speed of the signal. The oscilloscope has a maximum resolution of 1 nanosecond per subdivision, and the cursors can step in 400 picosecond increments. The electric spark discharge arc generated in air in the transmitter capacitor, i.e. the spark gap of the Windhurst machine, is aligned longitudinally with a laser to the receiver capacitor, ensuring that the maximum signal amplitude of the longitudinal impulse component is received and measured. The electric spark that is aligned generates a displacement current by discharging the previously charged direct current, or the DC capacitor, of the transmitter and the receiver, forming a total capacitance. The predicted longitudinal fluctuation signal component of the electric field with a propagation time delay of 5 nanolight seconds is based on the speed of light in a vacuum and can be measured in the near field by comparing the signals displayed on the two oscilloscope channels. The oscilloscope probe the oscilloscope probes on the transmitter spark generator is not touching the two spheres of the spark gap. Instead, a classic dipole antenna is used underneath the spark gap in close proximity to sample the signals. This ensures that the electric arc generation is not disturbed by the proximity of the oscilloscope probe, which could potentially damage the oscilloscope. The generator produces at least 300 kilovolts per centimeter of voltage before it discharges. The transmitter probe is connected to the dipole antenna, which, even though it is isolated, it is able to pick up the included impulse signal in the range of a few volts. So here we got some pictures.
Okay, that would be induced. And I have one other thing that's really catching my eye here. They're referring it to a paired capacitor. They're referring to it as a sphered capacitor. You see that it says spherical air dielectric cap when we go back up to, what is this, figure 2? The Mickey Mouse guys, the transmit and the receive. You guys know that, it's just like I covered on Globebusters on Sunday, that part of how you geometrically compute capacitance has to do with the area of the plates that are facing each other, not just their distance apart. And we're using spheres. So the part that is actually, quote, facing each other is infinitesimally small. You know what I'm saying? That there's almost no capacitance being shared here at all, because they're using round balls close together for purposes of creating the spark gap in an efficient, a tightly placed location in space on that electrostatic field longitudinal axis between them. But I think they're actually kind of shooting their foot, in regard to what kind of capacitance they really are sharing across this meter and a half. It struck me as geometrically inappropriate. I think that's about as succinctly as I can put this point. But you guys interpret it how you will.
All right. Let's see here. The electric spark is aligned and generates a displacement current by discharging the previously. Wait, did I already read that part? I think I did. Yeah. Yep, did that. And then now, yeah, we're down here at pictures. Okay. So here we have the Windhurst machines. Oops, with our spark gap situation going on over here. So there's our Mickey Mouse ears. And B. C. All right. Figure 3A, the electric discharge spark arc generated and signal sampled from the dipole antenna 10 centimeters underneath. B, the receiver capacitor uses a 2 millimeter ring spacer. The two spheres are placed on a neodymium 1 centimeter diameter magnet used to ease the installation. C is the photograph of the whole tabletop setup experiment. The oscilloscope in the center is not the one actually used in the experiment. This one was later replaced with another wriggle with the specs given here. 50 megahertz at 1 GSPS.
That's 1 giga samples per second.
1 giga samples per second. Nice, dude. That's my favorite sample size per second. I don't really like anything that's sub 1 gigi. You know what I'm saying? All right, the receiver oscilloscope probe was in electric contact with the receiver's spherical magnet capacitor. The air dielectric thickness of the receiver capacitor is 2 millimeters, and the spark gap in the transmitter is 8 millimeters. Both channels 1 and 2 input probes of the oscilloscope are connected with in parallel with a 1.5 VDC battery bias for the trigger level reference and low random frequency noise compression. Also, it is very important for this experiment that the receiver's spherical magnet capacitor sensor to be pre-charged at 1.5 VDC. Is that like volts per direct current or something?
It's volts of direct current. Yes, indeed.
Volts of direct current. Bias voltage for the spark generation occurs, or before the spark generation occurs. An electric discharge spark emanates a frequency spectrum that includes mainly blue visible light and invisible UV. It has been experimentally confirmed that it also generates radio frequencies, which can range from up to 150 kilohertz to 30 gigahertz, although they are commonly found in the range of 150 kilohertz to 10 megahertz. The signal of both the transmitter and the receiver detectors is passed through a RC low pass filter circuit before they are sent to the oscilloscope for measurement, as shown in figure 4. The cutoff frequency of the filter is set to about 2 megahertz in both filters in order to reduce the bandwidth for both the transmitter and the receiver signals. This helps limit the frequency of dispersion and distortion affected by the receiver signal caused by the nonlinear near field, referred to as the phase versus the KR graph in figure 11, the indoor reflections. At this time, it ensures that only the near field frequencies are measured by the oscilloscope probes, while the far field frequencies do not interfere with the signal group velocity measurement. This is important because the receiver signal should be less distorted as possible when compared to the transmitter signal in order for the impulse signal group velocity measurement to be reliable. We did not use the internal built-in oscilloscope filter because we wanted the filtering and bias to happen as close to possible as the transmitter and the receiver's sensors. So here we have their diagram of how that's set up. Figure 4, the LPF circuit schematic used in each oscilloscope probe. The filter is DC biased for 1.5 volts. The maximum probed frequency for the experimental setup mentioned is above 2 megahertz. At this frequency, the near field ratio is calculated as R over lambda equals 1.5 divided by 150 equals 0.01, which means that the wavelength is 100 times larger than the distance between the transmitter and the receiver. This puts us inside the very near field where we hypothesize that a longitudinal superluminal capacitor displacement current field exists. According to our theory, any signal for charge or discharge impulse is instantaneously transmitted, i.e., superluminally, between the parallel plates of the total capacitor's 1.5 meter length in air inner space, or in length, which is in air. All right. The aim of this experimental setup is to measure the speed of the charge displacement signal propagation between the inner field and the 1.5 meter dielectric capacitor filled with air. The objective is to demonstrate that the longitudinal field displacement current between the plates of an air or vacuum capacitor has an impulse signal speed, i.e., group velocity, that is practically instantaneous, which is faster than the speed of light. And this would prove that Maxwell's theory is correct about non-local displacement currents and that superluminal signal transmission is possible in the near field. In the experimental setup, both channel 1 and 2 of the probes of the oscilloscope, referred to as OSC for short, are positioned horizontally, polarized, and aligned with the dotted lines shown in the illustration of Figure 2. This is done to probe only the longitudinal displacement field capacitor current caused by the electric discharge of the arc spark created by the spark gap. Oscilloscope channel 1 probing transmitter will be used to trigger latching on both channel 1 and channel 2 channels of the both transmitter and receiver signal waveforms can be held off and displayed for comparison of the time delay. We are dealing with a signal impulse of finite duration, not continuous signals. So we will measure the group velocity of the two impulses, transmitter and receiver time delay, not the phase velocity of a continuous planar signal. Both impulse signals are measured at their own rise phase front. We expect the indoor reflections and interference to be minimal because of the single shot impulse nature of this experiment and not using a continuous signal. The oscilloscope hold off time is set to 1.5 seconds to further reduce the incoming environment reflections received and possible interference with the experiment. The complete set of settings for the oscilloscope during the experiment and also charging produced the complete set of settings used for the oscilloscope during the experiment and also charging produced of the Windhurst machine can be found here in section 1 or citation 1. In general, the maximum allowed measured signal propagation time and minimum speed of light, which Einstein's absolute speed of c of light is verified, is 4 to 5 nanoseconds, leaving a small 1 nanosecond experiment uncertainty margin. Any other result obtained less than 4 nanoseconds will be characterized as a null and instantaneous superluminal propagation in the near field. This is considered a control experiment, and we believe that no less than 4 nanoseconds measured is possible for conventional physics explanations. The entire experimental setup and apparatus are displayed in figures 3C. We conducted 3 8mm spark gap runs of the experiment with 3 spark measurements each run and 3 runs at 30mm spark gap settings. Balancing the transmitter and receiver wired oscilloscope channels. To ensure credibility of the experiment and the accuracy of the task, it is crucial to balance the 2 wired measuring paths, channel 1 and 2, which are connected with the transmitter and receiver signals. We conducted several control experiments to make sure that these 2 paths have an identical systematic time delay difference of less than 1 nanosecond. This was done to measure the spark radiation propagation speed of the 1.5 meter straight path distance compared to the 5 nanosecond time delay due to the speed of light 8c predicted by relativity theory. To transmit the signal to the oscilloscope at 1.5 meters, 1.5 meter long 50 ohm coaxial cable is used. At the other end, simple insulated wire with crocodile clips is attached, adding another 25 centimeters. There is also a 10 centimeter air travel time between the dipole antenna and the sensor and the spark gap. Were you about to say something, Stan?
I was. I was about to chastise them for using alligator clips on such a sensitive experiment.
How dare you?
Ghastly.
How dare you? All they had in the lab was alligators, my dude. Or whatever. All right, let's see.
Just couldn't afford a soldering iron. No.
All right, let's see here. We were right here. All in all, the total displacement of the transmitter path from the spark gap to channel 1 of the oscilloscope is 1.85 meters. The path from the sensor to channel 2 to the oscilloscope for the receiver is made up of 1.5 meters of coaxial and 50 ohm cable and a 33 centimeter simple wire totaling 1.83 meters. The length of the receiver channel wired oscilloscope path is made intentionally 2 centimeters less than that of the transmitter oscilloscope path to compensate for the fact that the transmitter oscilloscope signal travels 10 centimeters on air from the spark gap to the dipole antenna positioned underneath it, which is not the case for the receiver oscilloscope signal that travels solely on the wire, i.e., the speed of light on air is faster than the speed of light in an insulated wire. Both oscilloscope channels are filtered using the low-pass RC filter with a cutoff frequency of 2 megahertz, which is measured at both filters. In Figure 5, we present 2 block diagrams. One is shown in Figure 5a to depict the standard experimental setup. The second one will show Figure 5b illustrates the configuration used for the control experiment. The latter was designed to identify any potential imbalances of the transmission and the reception for the transmitter or the receiver, wired path, and the experimental leading to the oscilloscope. Wire path of the experiment leading to the oscilloscope. We got a picture here. Oh, this is the setup for the settings. Take a quick look at that. Put that.
And you'll notice that they did actually mention. They said, "Oh yeah, back in Figure 2, we labeled polarity when they didn't, and here they also don't. There's
Unlucky.
There's no polarity in this diagram." Oh well.
Dude, I guess we'll just have to guess, dude. The block diagram in Figure 5 is provided an approximation of the actual cable links used in the experiment. So we have A here, got our Wimhurst capacitive, spark gap adjustable 8 millimeters to 33. Yeah, no comment on the positive or negative there. Okay. Figure 5, the block diagram of the experimental setup, and Figure B is the control balance experiment. All right. The coaxial probe oscilloscope cables with an identical length of 1.5 meters and the impedance of 50 ohms were used along with the sample extension insulated wire with clips previously attached to sky. With the clips, do you notice how they didn't say alligator clips this time, Stone? They're trying to dampen the blow.
That's right. Don't pay attention to that. They're just clips. Wink.
The square of the wave reference signal is 1 megahertz was employed to detect the imbalance of the any imbalance existing between the total wire path for both channels, including their low-pass filters that were connected. So here we have the 2 time-sync channels, I believe. The imbalance measurement of the transmitter and the receiver, yellow and white, respectively. Oscilloscope wire paths include the connected LPFs. And that's
the low pass filters.
Yep, filters. In Figure 6, we see the most accurate measurement we could achieve with our oscilloscope. The 2 total wire channels, transmitter and receiver, including the LPFs, were measured at 10 nanoseconds over the deviation time based on...
That's 10 nanoseconds per vertical div going left to right on the screen.
Oh, okay, thank you.
Like every vertical set of dots is another 10 nanoseconds.
Yeah, got you. Yeah. I did not know how to interpret that. I was like, deviation? I don't know. Okay, so the div is based time based on the scale of the oscilloscope wires and were found to match. The yellow line represents the transmitter at channel 1, and the blue bottom line represents the receiver at channel 2. We visually estimate for an uncertainty of 1 nanoseconds from figure 6, where I reference the square signal of 1 megahertz. In figure 7, we have measured the actual imbalance we estimated previously with the transmitter channel leading the receiver channel 2 by 1.2 nanoseconds. This measurement is very close to the uncertainty of our experiment, which we set at 1 nanosecond. Okay. So we got some nice synchronized 1 megahertz blocks between transmitter and receiver. All right, figure 7, A and B, channel 1 transmitter and channel 2 receiver injected 1 megahertz reference signals and their measured parameters in C. A 1.2 nanoseconds has measured the imbalance between the transmitter and the receiver wire paths, including their filter passes, very close to the uncertainty limit, which was set for the experiment at 1 nanosecond. All right, Stone G, would you like to take over?
Yeah, I think we could do that. The small maximum imbalance found during the control experiment may have been caused by the random fluctuations of the continuous square signal that was injected from the generators to the 2 channels. However, this finding will not affect the conclusions of the single-shot actual experiment, which had an uncertainty set at 1 nanosecond to cover any unknown parameters, such as the characteristics of the transmit and receive sensors. We confirmed this through the actual experiment with the sensors connected, and in all our measurements, we couldn't detect any delay between the transmit and receive spark signal. To be thorough, we also swapped the wiring, probes, and low-pass filters connected to the 2 channels and obtained the same null result time difference between the 2 signals. Okay, there's Fig 8, and they're just showing you the reciprocal and that they look identical. Fourier analysis transforms the transmitting and receiving filtered spark signal measured, both showing similar harmonics content and spectrum, peaking at a dominant harmonic of approximately 2 megahertz. And A is your fast Fourier transform of the transmit signal, and B is the fast Fourier transform of the receive signal. Alrighty, in Fig 8 and 8b, we compared the Fourier analysis harmonics spectrum of the transmit and receive signals of a spark gap signal that we generated during the experiment. We found similar harmonics content and a dominant harmonic frequency in both signals at 2 megahertz. This ensures that the signals and information contained are suitable for comparison in our experiment. Additionally, it ensures that the receive signal is not heavily altered by reflections or other phenomena that could interfere with the experiment. And where's the results? In our measurements, we found no detectable time delay between transmit and receive signals down to the 1 nanosecond time scale. And Fig 9.10 here show a small sample of these results. Additionals in foot 1. Okay, 9a, transmit yellow on the top, blue on the bottom, signals generated by the electrical spark discharge, shown at 100 nanoseconds per div time. Oscillator base. B, transmit yellow on the top, receive blue on the bottom, just like before. Signals previously shown in Fig 9a measured at the 5 nanoseconds per div time oscilloscope base with 1 nanosecond visible subdivisions. Yeah, okay, great. Fig 9b, we used the oscilloscope's 2 vertical cursors, yellow for channel 1 transmit and white for channel 2 for the receive signal. The cursors were placed together with a 400 picosecond step resolution during the measurement. We determined that no time difference of the rise phase front of the 2 impulse signals could be measured due to the time resolution limitations of this particular oscilloscope model. They went cheap, they got the ghetto box, and it did not help them. Fig 10. Spark gap was discharged manually by touching a metal contact for an instant. A, the transmit, yellow on the top, blue for on the bottom. Signals generated. Null result. No measurable propagation time delay on air between the transmit and receive signals in the near field. The oscilloscope probes for this measurement were set both at the X1 setting. What he's referring to there too is with the X1 setting is it has to do with sensitivity and the number of volts that are transmitting through the probe wire. that there is no amplification going on here. Sometimes it's X1 and sometimes it's X10. And in a decent probe, right physically on it, on the solid part that you apply, to whatever the part of the project you're metering, there's actually a switch on it. And it just runs it through a different impedance through it to give you a different sensitivity by a factor of 10 in terms of voltage, which is really all oscilloscope does. It measures voltage over time. And that's what you're looking at on the screen here for every one of these things, including the fast Fourier transform analyses. They're really just looking at changes and rates of changes in voltage over time. Alrighty, Fig 10. We measured the signals by briefly short-circuiting the previously charged spark gap of the Wimshurst machine with a metal contact plate. Our 1 gigasamples per second digital scope allowed us to demonstrate an absolute null time delay difference between the transmit and receive signals. In particular, for this measurement, shown in Fig 10, to obtain shorter and cleaner signals for comparison, we used a metal plate, manually short-circuiting the gap and causing a violent discharge, which produced a spark at the contact points. The signal waveforms appeared quantized due to their relatively small strength and very short duration, which was less than 100 nanoseconds in total. Our findings support the results of previous independent researchers, all the citations here. They suggest that radio signal fluctuations propagate superluminally, as, for example, faster than the speed of light c in the near field. This behavior is attributed to the Coulomb longitudinal component contribution in the near field, i.e., within one wavelength distance. And the non-local nature of Maxwell's displacement current predicted within his theory of electromagnetism is also analyzed by Harass J. in citation 11. Our experiments confirm this superluminal behavior. We conducted a novel experiment that differs from previous ones, including Gasser W's work, by successfully isolating what we believe to be the longitudinal component of the Coulomb near field, which is also observed in the Maxwell displacement current of capacitors between their two plates or poles separated by a dielectric layer like air. In contrast to Gasser W's experiment, we took special care to align the transmit spark gap capacitance, the air gap capacitance, with the receive sensor capacitor along their length axis, using laser beam alignment to isolate the longitudinal component of the received signal. Also, we kept the distance as minimal as possible, and the spark signal generated power was much larger, ranging from 30 kilovolts at an 8 millimeter spark gap to 70 kilovolts at a 30 millimeter spark gap, compared to Gasser W's experiment, which produced sparks only at 10 kilovolts. Therefore, in our experiment, a much stronger signal was generated and transmitted during our measurements, resulting in a much stronger effect produced. The spark gap height was 1.75 meters from the ground. Furthermore, we low-pass filtered and constrained the bandwidth of our measured signals to minimize any interference from higher frequency harmonics or ghost images that could interfere with the experiment. This ensured that as much as possible, the direct transmit spark signal was measured as demonstrated in Figure 8. When conducting experiments involving the propagation of near-field static Coulomb field fluctuations, it's important to isolate the direct longitudinal air propagating component of the transmitted signal as much as possible, and prevent any far-field transverse electromagnetic waves from interfering with your measurement. To achieve this, a short distance and filtered setup is more suitable. However, such a setup requires more effort to control due to the short propagation time it imposes. Although the oscilloscope we used had both channels and both grounds fully isolated, as stated in its specifications, in order to address and make sure that no substantial signal ghost images were passing through the two isolated channel grounds, we repeated the experiments using a second separated oscilloscope and synchronized the two oscilloscopes together. We found again the same null result as before. A description of the two oscilloscopes setup experiment and a sample of the results can be found in this supplementary material repository here in citation 2. Okay, next, we present an analysis of the Maxwell theory of electromagnetism that supports the superluminal behavior we observed in the near field. And here we go, space campers. Theoretical analysis shows that according to Maxwell's equations, the inhomogeneous wave equation for electric field E, where ρ is the charge density, J is the current density, and C is the far field speed of light, like equation 2. Busy equals 4 pi out ρ plus 4 pi over c squared delta J over delta T. Isn't that fun? And again, the delta J over delta T is rather key in this formula. That is, again, the rate of change of charge, which is very important in regard to the total exchange of energy here. The longitudinal electric field solution for a harmonic oscillator dipole source, where omega is the angular frequency of the source, k is the wave vector, r is the distance from the source, and theta is the angle reference, the dipole. These guys have got a real hard time putting sentences together. There's equation 3 to make sense of that. The resultant phase shift of the longitudinal electric field is therefore theta equals kr minus, I don't know how you can put the tan to the negative 1 kr, and I wouldn't capitalize tan if that is indeed tangent, because they used cosine in the previous formula. I'm assuming that's what they mean. Anyways,
I want it to be a tangent because otherwise, or arctan, because then I can make sense of it. But without that, I
feel
nothing.
more comfortable. And it's actually to the negative 1, so it's an arctan is what they're talking about. It's kr minus the arctan of kr, which is really kind of weird. Anyways, that's the theta value for the resultant phase shift. And the speed formula below that, the group speed formula below that, the phase speed formula below that, and the group speed formula yet again below that, all derived out. Everybody loves algebra. Resultant equations for longitudinal electric field phase speed and group speed as a function of the product kr into equation 8 put onto 2 lines. They're just swapping brackets and having some fun with the divisor line. Okay, great. Here's your 3 that they were referring to before in figure 11. This is all versus the kr. K being the wave vector, r being the distance, and how phase and phase speed and group speed are changing according to that factor. Equations plots the longitudinal electric field E sub r, phase speeds C sub ph, and group speed C sub d versus the kr product parameter 2. There you go. Alrighty, the results shown in fig 11 show that the slope of phase versus distance curve for the longitudinal electric field has a minima at the source and becomes linear about 1 wavelength, lambda, from the source. Consequently, since the phase speed and group speed are inversely proportional to the slope of the phase versus distance curve, they are instantaneous at the source and reduced to the speed of light about 1 wavelength away from the source. And here's our conclusion. We report a null result or negative experiment result for a finite propagation delay of the near field displacement current of an air capacitor existing between its 2 poles, which was previously predicted and also experimentally verified by Dub Walker and the rest of the gang in general for propagating longitudinal near field radio signals, but is also predicted by Maxwell's theory for the non-local nature of the displacement current. We believe that both phenomena, Walker's generalization for superluminal transmission of radio signals in the near field and Maxwell's theory on non-local nature of the displacement current, are correlated for the near field. This experiment has led us to conclude that there is instantaneous or at least superluminal propagation within a 1 nanosecond uncertainty of our experiment on the expected 5 nanosecond value predicted by the known group speed of light and information speed. Therefore, we have a confidence level of 80% in our results. However, we must note that we were limited by short propagation time of the experimental setup and the capabilities of the oscilloscope used. In future experiments, it would be beneficial to include a picoseconds time-based oscilloscope or other measuring apparatus capable of measuring at the picosecond scale. Okay, this is scientist talk for appeal to whoever financed this thing, that we're going to need some better gear next time, so you better break out the wallet. That's what you're hearing right there.
The prototype phase.
Yes, if you really want to do this seriously, we're going to need an actual budget. I love it. Even though they had 2 scopes, they couldn't scrape one together that had the decent resolution to actually, appropriate to the experiment. I love it. It would also simplify the experiment setup and its unknown control parameters effects by using a single giant parallel plates air capacitor, shielded if possible, with its 2 plates separated at a sufficient distance. Now, what is sufficient? Do they quantify that? Hell no. That takes more money. By measuring the electric spark discharge signal propagation delay between its plates, we can determine the propagation signal speed of its Coulomb field existing in the air in between its plates at near field frequencies. Encouraged by these results, we predict that the research field of superluminality will play a crucial role in explaining some of the unknowns in physics, particularly in quantum theory. Oh, really? Buzz. This may help to clarify its apparent weirdness and incompatibility with general relativity. Oh, yeah. Yeah, Albert is kind of weird, isn't he? And could potentially serve as the missing piece in the puzzle from quantum gravity. I love it.
You know who
I
should fix
love
this
it.
shit?
They're like,
Albert, I bet.
Buzz.
Get him on the horn real quick.
Not me. I can't fix it.
This verbiage right here is almost as good as when you read in environmentally based papers and they talk about the benefits to climate change that could happen to further study. We believe that superluminal phenomena warrant further investigation and should not be easily dismissed. There will be both quantum interpretations and electrodynamic interpretations, which may differ. Well, I'm counting on it because one of them's bogus. Anyways, but the point is that in this experiment, information of the spark event arrived at the detector faster than a light speed propagating signal. This experiment clearly shows for the first time that information can be transmitted and received across space faster than light and can be used for superluminal, if not instantaneous, communication of information. Okay, right, I got to stop them right there because they talk about this near field and that it's all happening on the first wavelength. Well, how far away do you think someone can actually be to benefit from this type of communication faster than light? The other side of the room? Because any farther than that, it just cuts back to C, just like everything else propagating through physical space. So there is no benefit to communication, instantaneous or otherwise, coming down the road from this particular science.
But quantum weirdness, though, could be resolved in gravity or whatever.
Yeah, with this incompatibility thing, we better definitely fork out some more money and look more closely at this. Maybe we'll even label the polarity on our shit next time. Woo! Okay, so we won't bother with acknowledgments and declarations and stuff. Let's just call it a day.
I mean, I would like to extend my gratitude to Mr. Anastanosis's Echolulu for assisting during the experiment. Shout out to that guy.
So just another example of them trying to incorporate invariant speed of light.
No,
Light, I mean.
Well, they said that they measured, it not being what relativity predicts, but then also at the back end tried to like wrap it up as like maybe it's a mysterious quantum effect, so that we're not like super contradicting it. You know how they do the backpedal
Right,
stuff.
that's trying to explain it. Trying like another paper where they're like, "Ooh, this thing went faster than light, but it probably works. Don't worry about it." We haven't quite figured out how it works, but
have you heard of an Einstein-Rosen bridge? I think that's what happened.
Yeah, like there are smarter lads out there, so
I want to see how long it takes the guys forking out the money to figure that distance efficacy for this is purely dependent on wavelength, on frequency of the communication, the quote information that's supposedly being communicated here. That the higher they go in frequency, above 2 megahertz, for example, where current communication levels, you find them happening all the time. This is useful for shorter distances, the higher frequency you go. You know what I mean? There's this limitation that they place on themselves physically because of this quote near field calculation of wavelength. That it's working against itself. The higher frequency you go, the shorter distances this is actually useful at superluminal. I think maybe they might want to focus on communication across a PC board, like in a computer or something. If you wanted to transmit, you know what I mean, data bit place to place on a motherboard, somehow you could do that, but you'd have to set up extremely small, extremely high volt capacitors all over your board, constantly spark gapping to send that signal from place to place if you'd like to use it in this manner. Thusly turning PCs into lethal instruments misused. You know what I mean? So I don't anticipate much prospect at this particular part of science.
Yeah, great read. Awesome work. So you said that you were gonna bust out your oscilloscope and try and reproduce it, or what?
I need to take a closer look, and I think mine actually does 2 gigasamples per second. There's that.
Ooh, higher resolution, you said?
Yeah, double, baby, double. But I don't have anything that'll put out 2 megahertz in as far as a pulse width modulator. I'd have to think about how I would redesign one of them, build one of them, maybe buy one of them. Who knows? That would be interesting too. That's not my typical MO, but I could, I suppose. Yeah, it's possible. It is possible that can happen.
Nice. I would like to see that, and if there was perhaps a fundraiser to contribute to, that would be cool.
Ooh, once I ID a piece of equipment that's suitable, then maybe we could talk about fundraising.
Nice.
That would be also quite interesting,
Yes. Because it seems like this could be reproduced in terms of like just seeing if it's actually going faster than C, like even at those distances, just to like, fully solidify the quantification of a longitudinal wave, which, they said doesn't exist because, no ether, etc., and some other stuff. So that'd be cool to see how it works out.
Well, but for the Wimshurst machine, I got to admit the parts list is pretty short on this thing. So if I choose to use perhaps a flyback transformer instead and just hit it with maybe 24 volts or something and jump that to 12K and accordingly situate my physical geometry, we might get over the line on that cheaply.
No.
Yeah.
Nice, dude. Nice.
Yeah,
All right.
I think the Wimshurst machine's a distraction. It looks cool, but there's better ways to make it work.
That's how you get the money out of the guy who's financing it. You give him something cool that he can hand crank while you're doing your experiment. Oh, now we're really doing science here, bro. All right.
You feel that burning in your arm? That's science, baby.
We should calculate the calories while we're doing this.
You made that spark.
Oh, dude, that is a powerful sales tactic. But yeah, so that's awesome, man. Good read. We may be looking at a follow-up from Stone in the lab there, which would be awesome. So we'll go ahead and wrap up for the night, lads and ladettes. Tomorrow night, I'll be tapping in with Jaren from Jarenism, the flat earther formerly known as Jarenism, as we call him around here. So we'll be having a cosmological recap, going over the TFE and some of the stuff that I've found since then. And so we'll do that on tomorrow that'll be at 3 p.m. Pacific. So that'll be an early one in the day. And then on Saturday at 2 p.m. Eastern, Shane and I will be debating some check lads on the celestial theodolite and the old null hypothesis.